Hello students, this will be my last video on the topic capacitance, and today we will start with the effect of various mediums. If you change the medium between the plates of a parallel plate capacitor, then what will be the effect of that change on the capacitance of the capacitor? First of all, first is when conducting slab is placed. When you place a conducting slab between the plates of a parallel plate capacitor, then what will be the effect on it on the capacitance? So we have a parallel plate capacitor, this one, sorry, on the other side it will be negative charge. This is a parallel plate capacitor with electric field E0. E0 is the electric field between the plates of the capacitor. So this E0 will be equal to sigma naught upon epsilon naught. The formula for electric field between the parallel plates. This will be equal to Q upon epsilon naught A. Suppose Q is the charge, then it will be Q upon epsilon naught A. This is the electric field. The original capacitance C0 is epsilon naught A upon D, that we have already obtained. Here D is the distance between the gap between the plates. You can say distance between the plates or gap between the plates. So this is our original capacitance. Now here V0 is equal to E0 into D. V0 will be equal to V equals to E into R. So V0 will be equal to E0 into D will be equal to sigma upon epsilon naught, sigma naught upon epsilon naught D. This is equal to Q upon epsilon naught A into D. This is the original potential difference between the plates. Now we introduce a conducting slab between the plates with thickness T. Now outside the slab, the electric field is E0. Inside the slab, the electric field here in this part will be 0, because electric field inside a conductor is always 0. It will be like this. Negative charges will appear on this face and positive charges will be induced on this other face, and you will get a arrangement of this type. So electric field here in this part is 0, and in this part electric field is E0. So now the potential difference between the two plates of the capacitor V is equal to V0 into D minus T plus 0 into T. This open space, this blank space, here the potential will be V0. It will be, sorry, I have just a minute, it should be, this part should be E0. E0 into D minus T. In this part and this part, the electric field is E0. So potential difference of this part is E0 into D minus T, and here the electric field is 0, so the potential is 0 into T. So therefore we have V equals to E0 D minus T, which is equal to, now our E0 value is Q upon epsilon naught A into D minus T. This is V. Now capacitance C equals to Q upon V. So it is Q upon, for V we will replace this value, Q upon epsilon naught A into D minus T. Q will get cancelled and epsilon naught A upon D minus T. You can write epsilon naught A upon D, you can take common, 1 minus T upon D. This epsilon naught A upon D is C naught, and 1 minus T upon D. This is the expression for capacitance of the capacitor after introducing the conducting slab between the plates. So we have this formula, C equals to C naught 1 minus T upon D. Now 1 minus T upon D, this factor will be less than 1 because you are subtracting a value from 1, so it will be less than 1, and therefore C will be more than C naught. So the capacitance of the capacitor increases by introducing a conducting slab. Now, if suppose T is equal to D, if the whole space is occupied by the conducting slab, then this formula becomes, it will be C equals to C naught upon 1 minus D upon D. They both will cancel. C naught upon 1 minus 1, C naught upon 0 equals to infinity. So, if the whole space is occupied by the conducting slab, then the capacitance of the capacitor will become infinite. Means whatever charge you give to the capacitor, it will take that charge. Okay. Now next is, so this was about the conducting slab. Now, what will happen to the capacitance of the capacitor if we introduce a dielectric slab between the plates of the capacitor? So here we have this capacitor, and the electric field between the plates of the capacitor originally was E naught. Now we introduced a dielectric slab between the plates of the capacitor with thickness T. Then the electric field inside, as we already know that it will, in case of dielectrics, we have discussed that when a dielectric material is placed inside an electric field, polarization takes place and it develops an electric field in an opposite direction, and that electric field is EP, which will be generated in this direction, EP. So inside this slab, the electric field will be E naught minus EP. Now EP is P upon epsilon naught. So inside the slab, this is the electric field. Outside the slab, E naught is the electric field. Now again, the original capacitance is epsilon naught A upon D. C naught equals to epsilon naught A upon D. And V naught, as we have already obtained, is equal to E naught into D is equal to, it will be, just in previous that topic we obtained this value. It was E naught is sigma naught upon epsilon naught into D, and sigma naught is Q upon A. So epsilon naught A into D. This is the value of V naught. Now the total potential difference now here in between the plates is V naught in this region plus the V in this region, the region occupied by the dielectric slab. So it will be equal to E naught into D minus T plus E into T. E naught into D minus T plus E into T. Now you can write this as this is E naught D minus T plus T naught upon K into T. E naught upon K into T. Now you can take E naught common and you will have this value P upon K, just a minute, if you take E naught common, then it will be equal to d minus t plus t upon k. Now the value of E naught is equal to, E naught value is sigma naught upon epsilon naught, and sigma naught will be q upon epsilon naught a. So you will write q upon epsilon naught a d minus t plus t upon k. Therefore the capacitance, new capacitance, is q upon v. So q upon epsilon naught a into d minus t plus t upon k. Now q will get cancelled, and this is E naught a epsilon naught a, and you can take d common, 1 minus just a minute. So we get this formula, epsilon naught a upon d minus t plus t upon k. This is our C, the value of C. We can write it like this: C equals to epsilon naught a upon d minus, you can take t common, 1 minus, it will be 1 upon k, 1 minus 1 upon k. So this is the, you can say this is the final formula for capacitance. Now suppose we insert a dielectric slab such a way that its thickness is equal to the gap between the plates, means T is equal to D, then C becomes epsilon naught a upon d minus d into 1 minus 1 upon k. This will be equal to epsilon naught a upon, you can take d common, 1 minus 1 plus 1 upon k. This epsilon naught a upon d will become C naught, and 1 and minus 1 will get cancelled, 1 upon k equal to k times C naught. So if the whole space between the plates is occupied by the dielectric slab, then the capacitance becomes k times, where k is the dielectric constant of the material. Now we move on to the section uses of a capacitor, and the main uses are to produce electric field of desired nature. You can produce an electric field of desired nature with the help of a capacitor. For example, like for oil drop experiment which was conducted by Millikan. So in such type of cases, you can produce an electric field of desired nature with the help of a capacitor. Okay, the next is, second important use is, it is used in the radio tuning circuits. In radio tuning circuits. Third is in power supplies for smoothing the rectified current. Rectified current. Rectifier is a device that converts DC, that AC into DC, sorry. A rectifier is a device that converts AC into DC, but the output which we get is not a smooth DC, it is actually a pulsating DC. So to smoothen that DC, to make its my value means to smooth to remove that pulsating nature of the DC, we use this capacitor. We call that circuit as a filter circuit. So rectified current in filter circuits. So we use this capacitor in making the filter circuits. Now next is for producing rotating magnetic fields in induction motor. Rotating magnetic fields in induction motor. To produce rotating magnetic fields in the induction motor. Next is in the tank circuit of oscillators. Tank circuit of oscillators like an LCR oscillator. LC oscillator, sorry, not LCR, like in case of a LC oscillator. L is for inductor and C is for capacitor. So we use capacitor in making the LC oscillators. Next is they do not only store the charge. The capacitors not only store charge but they store the energy also. And that energy can be used in various different can be used for the various purposes. So these are the main uses of capacitors. Okay, next is effect of dielectric on various parameters, and we will discuss this topic in two conditions: when the battery is disconnected, or battery remains connected. Suppose we charged a capacitor with the help of a battery. And now what will be the effect on its various parameters if we disconnect the battery after charging and we keep the battery connected even after the charging also, in these two different cases. So here in this case, when the battery is disconnected, the charge will be equal to if you disconnect the battery, no further charge the capacitor will receive, and the charge will remain equal to the charge whatever it has received. So Q equals to Q naught. This will be it will remain constant. Here the charge will become K times, where K is the dielectric constant of the material. Next is V equals to V naught upon K. The potential difference, if you remove the battery, then the potential difference becomes V naught upon K, 1 upon K times the original potential difference. But here V is equal to V naught, because a battery maintains the potential difference between the plates of the capacitor. If you keep the battery connected, then it will maintain that potential difference. So V will remain V naught. Now since V changes in this relation, so E also becomes E naught upon K, and here E remains E naught. Electric field will remain same because, as we have discussed, because the potential difference is changing in this ratio. So here it is constant, so electric field will remain constant. Here potential is changing 1 upon kth time, so the electric field will also change in the similar way. Now capacitance here becomes K times, and capacitance here becomes K times. The capacitance in both the cases will become K times the original capacitance. U here becomes 1 upon K times, and U here becomes K times. U is the total potential energy of the capacitor. So if you disconnect a battery, then charge will remain constant, will be Q naught. V, E and U will become 1 upon K times. If you keep the battery connected, then charge becomes K times. V and E will remain constant, U will become K times, and capacitance in both the cases will become K times. Now next is capacitance of a parallel plate capacitor with the compound dielectrics, and we can have the dielectrics, the combination of dielectrics in two different ways. First is series combination of the dielectrics. Series combination is like this. Suppose we have the plates, so these are the different layers of the dielectrics with K1, K2, K3, K4, like this. We have different layers of dielectrics, different type of dielectrics we have, and they are connected in such a way that the first layer is connected to the to one plate, the other end of that layer is connected to one layer of the next dielectric, you can say dielectric layer, and similarly like this. So here in the figure it is clear. It is in such a way. If you have like this, if you have this way, where each and every dielectric slab is touching both the plates, then this type of arrangement will be called as the parallel arrangement or parallel combination. So first of all, we will find out capacitance in case of a series arrangement. So for a single dielectric, we have obtained the formula C equals to C naught upon, it will be, you can write the previous one formula. The formula was D minus T of D minus it was I think the formula was D minus T plus C. Yes, it was like this: D minus T plus T upon K. So we obtained this formula just now, that C will be equal to epsilon naught A upon D minus T plus T upon K. Now for the series arrangement, if you have series arrangement, then this epsilon naught A will remain same, D will remain same, and this T will be the total thickness of all the dielectric slabs will be T1 plus T2 plus Tn. This will be the value of T, plus this will be T1 upon K1 plus T2 upon K2 plus Tn upon Kn. This T will become T1 plus T2, similar like this, and here also. Now this is the total thickness, and you can take it equal to D, and this D will get cancelled, so you have formula E upon A T1 upon K1 plus T2 upon K2 plus Tn upon Kn. This is the formula for capacitance with series combination of dielectric slabs. Now we move on to the parallel combination. Now, as we already know that in case of a parallel combination, we have C equals to C1 plus C2 plus C3 plus Cn. The sum of the individual capacitances will be equal to the total capacitance of the of the arrangement. Now we have C1 equals to K1 epsilon naught A upon D1. Suppose we have A1 upon D. They have different areas A1, A2, A3, AN, but this length will be equal D. So you will write K1 epsilon naught A1 upon D plus K2 epsilon naught A2 upon D and Kn epsilon naught An upon D. The sum of the individual capacitances. Now you can take epsilon naught upon D, you can take common, K1 A1 plus K2 A2 plus Kn An. You can take epsilon naught A upon D common and this will be the value. Now let us suppose that if A1, if they have equal areas, A3 equal to An, then this will be equal to A upon N, where A is the total area of the plates. So A upon N. So this formula will become C equals to epsilon naught A upon D into N, which will be equal to C naught upon N. This will be the value. Just a minute. I will change this value. Sorry, it will be like this. We have to replace it here. Epsilon naught A upon N D. A upon N, A upon N, A upon N. You can take that A upon N common and will be K1 plus K2 plus Kn. Now this epsilon naught A upon D is C naught upon N, and this is K1 plus K2 plus Kn. So here we finish the first two chapters of your NCERT book and the complete part of electrostatics. Thank you.